first portion of these practice problems, we're taking this area, which is the area under x squared plus 1 between y equals 0, x equals 0, x equals 1, and y equals 0. So the yellow area, we're going to rotate it about different axes using different methods. Then we're going to rotate it about these two axes using any method that you choose. In these cases, it's wisest to let the area dictate the orientation of your element. Obviously, it's going to be easier to have your element vertical than horizontal, because if you have horizontal, you have to stop here at x equals 1 and then start up again from 1 to 2 with a different length of your element. So let's get started. First, we're going to rotate about y equals 0, and we're going to use the disk method. So y equals 0 is the x-axis. Disk means perpendicular, so our element is vertical. That means we're going to be using a dx. And y equals x squared plus 1 is our function. X is going to go from 0 to 1. So we have our limits. Disk method is pi r squared, and dx is the h. So the radius is the distance from the axis to the curve, and that value would just be the function itself. So the first thing you need to do is simplify your integrand. So you're going to FOIL this out. Don't be lazy. We still have to integrate after we simplify. Don't forget to integrate. So here we have FOILed method here. Integrate, add 1 to the power, divide by the power all the way through. And now you're ready to plug in your limits. You're going to go from 0 to 1. Notice that this is a polynomial with no constant, so when we plug in the 0, we get a 0. Plugging in the 1, I get 1 over 5, 2 over 3, and a 1. Now I have to get a common denominator, which is going to be 15. So if everybody's over 15, I multiply this by 3, this by 5, and this by 15. Sum everything up, and I get 28 and a pi over 15. For number 2, we're going to rotate about the same axis, but we're using the shell method, which means we have to be parallel to the axis. That's going to dictate that our elements are horizontal. That means we have to split this into two separate integrals, from 0 to 1 and from 1 to 2. And the height of our elements will be different in those two regions. So the first part, we're going to integrate, by the way, it's 2 pi rh. We're going to integrate from 0 to 1. These are dy. So the radius is the distance from the axis of rotation to the element. That means the radius is going to be the y value minus 1. So it's just plain old y. Sorry, minus 0, you know what I mean. The height of these elements is the top minus the bottom, so 1 minus 0, which is just 1. And this is dy. Plus, now we're going to go from 1 to 2. The radius is still going to be the y value, and the height is going to be this side, 1 minus the curve, but we have to have the curve in terms of y. So if y equals x squared plus 1, I subtract 1 from both sides and then take the square root of both sides to get x equals the square root of y minus 1. But notice that the height is going to be 1 minus that distance right there. So 1 minus the square root of y minus 1 is my height. Ew, that's going to be awful. The second integral is going to be rough. So once I plug in my height, 1 minus the square root of y minus 1, notice that in this second integral, I can multiply the y times 1 and just do that integral. Then I can multiply the y times the root and do a separate special substitution integral. This guy right here, integrating y, I get y squared over 2. The 2's are going to cancel. I'm going to plug in the 1. I'm just going to get pi. So that part was easy, so we got that done. Now this part right here, like I said, take that y and multiply the 1 and do that integral. Because the second part is going to be a difficult substitution integral. Okay, this first one is just going to give me y squared over 2. It's going to look just like this. So I have 2 pi y squared over 2. The 2's cancel. I'm going to plug in the top minus the bottom. Always leave the hardest thing for the end, right? So you can focus just on that. In this case right here, the 2's cancel. Plug in a 2, I'm going to get a 4. Plug in the 1, I'm going to get 1. That's going to leave me with a 3 pi for this piece right here. So this total is going to be a 4 pi. Now over here, we're going to have to do something special. Sorry, my talking and my writing are got to catch up to each other. In this case right here, it's going to be, the derivative of the stuff under the radical is just dy. I have an extra piece. So I'm going to let u equal the whole square root. And then when I square both sides of this equation and add the 1, I get y equals u squared plus 1. Take the derivative of this and I get dy equals 2u du. When I plug all of that stuff in and I integrate again, I'm going to need to change these limits if I'm going to change it to u, right? So looking at this equation right here, if y equals 1, then u equals 0. And if y equals 2, plug a 2 in here, I get the square root of 1, so u equals 1. That changes my limits. It's actually going to make everything much easier. So now I'm going to integrate, instead of from 1 to 2, because I'm doing it with u, I'm going to integrate from 0 to 1. This piece right here is u squared plus 1. The square root is plain old u, and dy is 2u du. When I multiply all of this out, the 2's going to come out and make that a 4. I've got u squared distributed through here. So I'm going to be integrating from 0 to 1, u to the 4th, plus u squared. Simple integral du. So now I've taken this big nasty and made it just a simple power rule integration by doing that u substitution. So I have u to the 5th over 5 plus u to the 3 over 3. Be careful plugging in your numbers. You're going from 0 to 1. So you've got the 4 pi in front minus 4 pi times. Plugging in the 1, you get 1/5 plus 1/3. Plug in the 0, you get 0. So common denominator in there is going to be 15. We have the 4 pi in the front minus 4 pi times. Getting a common denominator, multiply this by 3, this by 5. I get 3 and 5 is 8. The 4 times 8 is 32, but I got to multiply this guy by 15 over 15. So this is going to be 60 pi minus 32 pi, and that's going to give me an answer of 28 pi over 15, which is the same thing we got last time. Sorry. Okay, for number 3, we were going about a different axis. X equals 0 means we're rotating about the y-axis now. We're told to use the disk washer method, which means our elements must be perpendicular to the axis of rotation. So I'm forced to do dy here. Same situation as the last one. We have to split it up where the edges change from being just 0 on this side to being the curve itself. We have to use a dy. Washer is pi r squared minus the inside pi r squared. So here we go. From 0 to 1, I'm just integrating a radius of 1. Pi radius squared, it's dy, and y is going from 0 to 1. And then the second bit, once we cut it off, we're going to go from 1 to 2 on y. It's pi, the outside radius squared, minus the inside radius squared. So the outside, remember this is our axis, so the outside radius is this whole distance, which is a constant 1. The inside radius is the curve. The curve was y equals x squared plus 1, but remember we have to have it in terms of y. So when you take this equation and solve for x, that's the distance here horizontally. So I have the outside radius minus the inside radius. This is not FOILed out. It's 1 squared minus this squared. When I square this, I get y minus 1. I'm subtracting the whole thing, so that minus has to be distributed. So the ones don't cancel, they double. So here's my new integral, which is easy. This part was easy, I just get y. This part, I'm going to get a 2y minus y squared over 2. This part was from 0 to 1, so I get plain old pi. This part right here, when I integrate it, notice that I'm not plugging in a 0 here, so be careful. I plug in a 2, I get a 4. Plug in a 2 here, I'm going to get 4 over 2. This is going to give me plain old 2. When I go to the 1, I'm going to plug it in here and get a 2. Plug it in here, I get a half. Remember, you're subtracting the top minus the bottom. So that minus gets distributed here. So this is a 2, this is a minus 2, and that gives me plus 1/2. That means this whole thing is just 1/2. So I end up with the pi in the front, and then the pi over 2. Put them together, I get 3 pi over 2. Same axis of rotation, the y-axis, but we are going to do the shell method. That means my element is parallel to the axis. So I'm doing this one in dx. It's a horizontal. That means the top is always the top, right? And the radius is the distance from the element to the axis of rotation. That's just the x value. And remember, the shell method is 2 pi rh. R is x, h is going to be the height of the curve, and we're doing it with dx, so x squared plus 1 is sufficient. We are integrating along the x-axis from 0 to 1. R is x, height is x squared plus 1. We're doing it with respect to x. I'm going to distribute the x, and now my integral is going to be from 0 to 1, x cubed plus x dx. So when I integrate that, I'm going to get x to the 4th over 4 plus x to the 2 over 2 on 0 to 1. Plugging in the top number, I'm going to get 1/4 plus 1/2. Plugging in the 0, I get 0. Common denominator, I got to multiply this guy by nothing and this guy by 2 over 2. So I'm going to get 1 plus 2 in the top, which is 6. And the 2 on the outside in front of the pi is going to cancel with the 4 in the denominator. And that's going to be 3 pi over 2, which is what we expected. Okay, now same area, but we're rotating it about the line x equals 2. we're to pick our own method, we obviously want our element to be vertical so that the top is always the top, the bottom is always the bottom. We have the curve on top and the axis on the bottom here. So that means my element is parallel to my axis. I want to use the shell method, 2 pi RH. Now, your radius is not the distance from here to here, but your distance from the axis of rotation to the element. Well, this distance is x. That makes this distance 2 minus this much gives me this much. So the radius is 2 minus x. The height is just the curve. So we set up our integral. We're doing dx. So 2 pi x goes from 0 to 1. The radius is the blob 2 minus x. The height is the blob x squared plus 1. Everything's with respect to x, and I have to FOIL that out before I integrate. Don't try to integrate without doing the simplifying. So 2 times the x squared, negative x times the x squared, 2 times the 1, negative x times the 1. You may get your terms in a different order, but it doesn't matter. Integrating term by term, I get 2x3 over 3 minus x4 over 4 plus 2x minus x squared over 2. That gets evaluated from 0 to 1. Obviously, when I plug in a 0, I'm going to get a 0. So all I need to do is plug in the 1 and then get common denominators. So 2/3 minus 1 over 4 plus 2 minus 1/2. Common denominator is going to be 12. So I'm going to get 2 pi, put everything over 12. This guy gets multiplied by a 4, which is going to make that an 8. This gets multiplied by a 3, this by a 12, and this by a 6. Be careful with your numbers. So the 2 pi on the outside is going to cancel with the bottom. I'm going to end up with a 6 in my denominator. But the top here is going to be 5 and 24 and minus 6. So I'm going to end up with 23 over 12, cancel the 2 and the 12, 23 pi over 6, and I'm done. About the axis y equals -1, rotating here, we still want to have our element vertical. So that's perpendicular to the axis. That means I have a washer. Why is it a washer instead of a disk? You have that hole in the middle. So I'm going to have pi and the outside radius squared. Well, this is the curve, and this is an extra 1. It's the curve minus the axis. So the curve is the function minus a -1 gives me +1. I end up with x squared plus 2. And that's radius. It gets squared in this method. Don't forget your dx on there. The inside radius is the distance from here to here. It's 0 minus -1 or plain old 1 and a dx. All right, this has to be FOILed, and then we're going to combine like terms. So I'm going to get x to the 4th plus 2 times 2x squared plus 4 minus 1. That's going to give me a 3 right there. Integrating term by term, x to the 5th over 5 plus 4x to the 3 over 3 plus 3x. Now when I plug in the 1, I get value, but when I plug in the 0, I get 0. So I get a 1/5 plus 4/3 plus 3. Need a common denominator, which will be 15. So pi times 15 on the bottom. I have to multiply this guy by 3, multiply this guy by 5, and multiply this by 15. Adding it all together, I'm going to get 68 pi over 15. Okay, now we're going to do some problems with arc length and surface area. Notice that for the arc length, I'm asking you to just set up the integral, okay? You've got the curve square root of 1 minus x squared on the interval 0 to 1. For the arc length integral, you have to set up this integral. Let me write this down real quick in blue. Arc length is, from the beginning to the end, the square root of 1 plus the function prime squared dx. So we have the function right here. It's blob to the half. I'm going to take the derivative of that. So 1/2 blob to the minus, spit out the derivative of the stuff in the parentheses. The 2's are going to cancel. I get minus x, and now divided by the square root. This has to be squared to plug in right here. So we square this, the minus becomes a plus, x squared, and the root goes away on the bottom. Now I have to take the square root of 1 plus that thing, which means I have to get a common denominator. So when I bring this up to the top here, multiplying by 1 minus x squared over itself, I get this, minus x squared plus x squared, boom, I get this thing, and we have this. The arc length is the integral from 0 to 1 of this thing, the square root of 1 plus the derivative squared dx. And when you get to chapter 8, you'll be able to integrate this, but for now we're just setting it up. Now rotate that curve about y equals 0, or the x-axis, and find the surface area. Well, we still need the arc length part, so this is the same thing we got before, but now we're going to have, hold the phone, we need surface area is 2 pi integral from a to b of the radius times the arc length portion, 1 plus f prime squared dx. And we're just doing everything with respect to x to make it simple here. Focus on the radius. The radius is the distance from the axis of rotation to the curve. In this case, because we're doing dx, we're going to use the curve as our radius. So when we set this up, here's the radius, and here's the arc length portion. Those guys cancel out, and you're just integrating dx, which is going to give me 2 pi x from 0 to 1. I end up with a plain old 2x. Now, if we rotate about the same curve now about the line x equals 0, that's the y-axis. We're going to use the same arc length portion, but now my radius, if I'm doing it with respect to x, the radius is the distance from the y-axis to the curve. Well, that's just the x value. So when I set that up, here's my radius, and here's my arc length portion. It's the square root of this stuff in the denominator. So the square root is the half power, minus means it's in the bottom. So this is going to be a simple substitution integral where I set the inside of the parentheses equal to u and take the derivative of that and see that I need a minus 2x dx. Well, I have the x and the dx. I'm going to multiply by a minus 2 to create a perfect du. But if I multiply by minus 2, I have to divide by minus 2 as well. So this thing out here becomes minus pi. Integrating blob to the power derivative of the blob means I'm going to add 1 to the power and get positive 1/2 and divide by the positive 1/2. Dividing by a fraction flips that 2 up to the top. I end up with a minus 2 pi on the outside. This piece right here is just the square root. When I plug in a 1, I get 1 minus 1. That's a 0. When I plug in a 0 to a substitution integral, it doesn't go away. I plug 0 in here, I get the integral of 1, which is, the square root of 1, which is just 1. So that minus sign on the front is going to get canceled out here, and we end up with a positive 2 pi surface area.